you expect to get as a shareholder. All right, let's do some examples. So for these examples, my hope is that you pause, you read through the example, and then you try to set it up and solve it for yourself. And at the end of the lecture, you can check to see how I have set these problems up and check the correct answer so that way you can figure out where it's tripping you up. So please don't just look at the answer and then try to reverse engineer the question. Okay, so your new 30-year 5% APR mortgage requires payments of $40K per year starting next year. How much does your house cost? So what do we have? We've got our C, which is 40K. We've got our R, which is 5%, 5% APR. And we also have our N. We know that this is going to be for 30 years. So we can just set it into our annuity formula and find the present value. Part B, what would be the value of this house today if you had to start making your payments in exactly 5 years? So in this example, one of the things that we want to remember is that these are always, our present value is always starting next year. So when we set this up, we'll take the present value that we saw for in part A, and now we're going to discount that present value by 1 plus 0.05 to the power of 4, because we're always wanting to acknowledge the fact that it's next year. That may not make sense as I say it to you, but as you set it up and solve for it, you'll see as you do the math. Okay, you want to pay off your 1M home over 20 years, starting next year using a 6% APR mortgage. How much do you have to pay per year? On our left-hand side, we've got our 1M. On our right-hand side, we know a few things. We know our APR, and we also know our N. So we know that our discount rate is 6%, and we know that our time period is 20. The thing that we don't know is C, the level of payment that we'll have to make every single year. So that's exactly what we're solving for. So hopefully what you can take away from these examples is that we can always use what we have in this formula to solve for the thing that we don't. Okay, example 2. Your family has a perpetual trust fund that pays 100K per month starting next month. The fund is in an account that offers 1% interest per month. How much is the fund worth today? Remember, this is a perpetual fund, meaning that it's always going to be paying 100K per month, and it starts next month. This is very clearly an example of a perpetuity, so we can plug it into our perpetuity formula to find the present value. Suppose instead that the fund begins paying 100K per month 13 months. How much is the fund worth today? So what do? We take our solution from step A, in which we solve for the present value of that fund, and then we discount it. But remember, whenever we discount, because this is going to pay 100K per month in 13 months, we're going to be discounting by 1 plus R to the power of 12, because our first period is always times 0. So please don't let that trip you up. Sometimes it can be a little bit unfamiliar if it's not something that we've done a lot in terms of valuations, but we always want to remember our first period is period 0. Okay, you've taken out a 500K loan. You will never pay back any principal on this loan, but you'll always make the interest payments of 8% per year. Suppose you get a tax credit of 40% of your interest payment. That is, the government gives you back 40% of the interest you pay out every single year. What is the present value of all your tax credits? Assume your discount rate is the same as the cost of debt, which is 8%. So what do we have? Step by step. This is a great example of the tax shield value of debt, and we'll basically think of this as one of the benefits to holding debt, and this is arguably one of the reasons why we would expect companies to use leverage. So this is a perpetual bond, meaning that the company's always going to be making interest payments on this debt, but it's not going to be something that's ever paid off. It's not going to be amortized. All right, step by step. We've got our 500K. We want to know what our interest is. Well, our interest payment is 8%. Cool. So we take our 500K, we multiply that by 0.08 to get 40K. Our next question is, well, what's the tax credit? What's the tax write-off that we get? We don't get to write off the entire 40K. We do get to write off 40% of the 40K. So that's why we have 40K multiplied by 0.4. Now, here's the part that might surprise you. That 16K, that's our annual tax write-off. Now, if we're assuming that we'll be writing this off forever, then we're going to do the perpetuity formula. So we take our 16K and we divide it by 0.08. And what do we find? What we find is that this 500K loan that we've taken out, this perpetual loan, actually has a present value of a tax credit of 200K. And that's because forever we're going to be using our 16K write-off. And at the present discount rate of 0.08%, it's a perpetuity that has a value of 200K. All right. We've been talking quite a bit about ordinary annuities, ordinary perpetuities. Annuities and perpetuities can also grow. So a growing annuity is a stream of cash flows over a finite time period that grows at a constant rate of G. So hopefully there's kind of two things that stick out when we look at the growing annuity formula. We still have C, our cash flow. So we've got our constant cash flow, but now it's being divided by R minus G. R is our interest rate and G is our growth rate. Right off the bat, let's just kind of establish this. Suppose that my discount rate is 10% and my growth rate is 5%. If I'm dividing a number by 10 minus 5%, so now 0.05, versus me dividing a number by 10%, so 0.10, whenever I have R minus G, I have a smaller number in the denominator. Smaller number in the bottom means that I have a bigger number when I actually divide it. So what am I telling you? What I'm telling you is right off the gate, you can see that the present value is going to be higher the higher the growth rate. We can also see that when we look inside the annuity factor. 1 minus 1 plus G divided by 1 plus R, well, 1 plus G is already higher than 1. When we do a ordinary annuity formula, we're essentially putting 0 as our growth rate. And if you don't see that, hopefully what you can see is R minus 0 equals R and 1 plus 0 equals 1. Okay, so you already were doing a growing annuity formula. You didn't even know it. It just happened to be the case where the annuity would grow at a rate of 0. The growing perpetuity formula, same idea. We've got C divided by R minus G, and we'll see in the examples that we do next is that whenever we have an annuity or a perpetuity that's growing, its present value is going to be that much higher. So let's do an example together. A firm is considering a project that provides cash flows for 30 years. So we already know what's an annuity. The cash flow in the first year is estimated to be 10M, and cash flows are expected to grow by 5% per year for the life of the project. Suppose that the project's cost of capital is 12%. What is the value of the expected net cash flows generated by this project? So what do we have? We've got our 10M, that's our C. We got our R, that's 0.12, and we've got our G, that's 0.05. So we have our first part set up, and then we have that whole entire thing, our whole entire equation multiplied by 1 minus 1.05 divided by 1.12, 1.05, again, 5% is our growth rate, 12% is our discount rate, and that entire fraction taken to the power of 30, and then we multiply that out. Okay, part B. You plan to hold the stock in perpetuity. You expect that the first dividend will be $2.50 and it's going to be paid next year. And you expect dividend payments to grow by 4% thereafter. Your expected rate of return for the stock is 10%. What are you willing to pay for this stock today? So we've got a perpetuity. It's going to be a dividend that pays 250. We expect the dividend will grow at a rate of 4%, and our discount rate for holding the stock, our expected rate of return or required rate of return is 10%. So we've got 250 divided by 0.10 minus 0.04, and behold, we have a present value of $41.67. Okay, so our second concept is going to be discount rates. So we've already seen thus far two really important things. One, we've reestablished how to use our present value and our future value to account for the time value of money. We know that if we have a set of cash flows that are varied, meaning in one year it's 10M, and another year it's 8M, and the last year it's 13M. If all of our cash flows are varied, we're going to discount those one by one. We know that if our cash flows are constant, we can use our annuity formula. If our cash flows are constant but grow at some rate, we can use our growing annuity formula. The other thing I want to point out that sometimes can be a bit of a jump if we're not used to doing valuations is that our perpetuity formula, we have C divided by R. So if it's a cash flow that's going to be happening forever, then I've got my cash flow divided by my discount rate. If it's one cash flow that's happening next year, then I want C divided by 1 plus R because it's not a perpetual cash flow. It's a one-time cash flow. Okay, so in all of these, we've been assuming that our discount rate is just given to us. And now we want to be a little bit more attentive to our discount rate. So the discount rate R need not be on an annual basis. You can have a discount rate on a quarterly, monthly, and as we'll see with many of the settlements for futures, on a daily basis. So how do we get from our annual to our higher frequency? We divide. Suppose our annual interest rate is 12%. The quarterly interest rate is going to be that 12% divided by 4. So our quarterly interest rate will be 3%. Suppose our annual interest rate were 12%. Well, then our monthly would be 1%. It would be the 12% divided by 12. Suppose that our annual interest rate were 12%. Well, then our semi-annual interest rate would be 6%. It would be the 12 divided by 2. So we can always chop up our annual rate to find the appropriate frequency with our discount rate. And what's the intuition? Well, we always want to make sure that M, the number of compounding periods, it could be quarterly, monthly, daily, whatever. We want to make sure that our M matches the frequency of our cash flows. So let's look at that. We'll typically be working with annual cash flows and annual interest rates, but our discount rates can also be quarterly and they can be monthly. And sometimes the data that we'll get from financial press and financial databases will have quarterly or monthly interest rates. So we always want to make sure that we're using the appropriate discount rate. So when given annual rates, in our previous example, we said an annual rate of 12%. What do? If we have cash flows or if we have a period, let's say that in this example, it's quarterly, we would take I nominal, which would be 12%. We would divide it by 4. So we would get our 3%. So it'd be 1 plus 3%. But then when we compound it, we would also want to take into account that it's compounding over a higher period of frequencies. So in our previous examples, let's say that we're solving for a future value 3 years from now. Well, 3 years is actually 12 quarters. So in this example, it would be m equal to 4 and n equal to 3, because we would want to acknowledge that every year we have multiple periods in which our rate of interest is compounding. So it feels more wordy and it feels like a lot more steps, but intuitively, as you set this up and as you solve for it, it'll feel very, very natural. So let's look at an example. We've got $100 at a 12% rate, where it's going to be semi-annually compounding for 5 years. So on my left-hand side, I'm solving for the future value. Notice that we have 5 and we put S because it's 5 years, but this also going to be semi-annual. Okay, my right-hand side, I've got 100. I've got 100 plus 100 multiplied by 1 plus 0.12, the 12% divided by 2 because it's semi-annual. And then my exponent, it's 2 times 5, 2 half periods within the year multiplied by 5 because it's going to be happening over the course of 5 years. All right. We can also solve for the interest rate. So hopefully what you take away from this, previously when we set this up, we were trying to find out what's the period, what's the n that's going to double our money. Now we're saying for a given length of time. So in this example, what annual interest rate would be needed to double your money at the end of 3 years? So for a given length of time, in this case, 3 years, same setup. Left-hand side, we've got 2. Right-hand side, we've got 1. If we wanted to triple our money, left-hand side would be 3. Quadruple, it'd be 4, etc. And in parentheses, we've got 1 plus I. So it's the exact same idea, exact same tools. The big takeaway that hopefully you're getting from this is that whenever we have parts of our equation that we know, we can use those to solve for our unknown, for the part of our equation that we don't. Let's put it all together. A firm is considering a project that will generate quarterly cash flows of 3M for the next 15 years. Suppose that the firm's annual cost of capital is 16%. Okay, so a few things will hopefully jump right off the bat. 3M, that's our cash flow. The next 15 years, okay, but this is a quarterly cash flow. So it's 3M every quarter. And those 15 years are going to be 60 quarters. So let's put it into our annuity formula. What do we find? We've got 3M divided by our discount rate. In this case, we took our 16% and divided it by 4. Why? Because our 16% is an annual rate. And what we want is our quarterly rate because we're getting quarterly cash flows. So hopefully everything feels intuitive as we set it up and solve it out. And as we do the math, you'll notice that we took it to the power of 60 because we have 4 quarters per year for the next 15 years. So 4 times 15. Part B, suppose the cash flows are projected to grow at 1% per quarter. What is the present value now? Again, take your calculator, take a pen, take a paper, set it up, solve it out, do it step by step, and confirm that you're able to get both of these answers. Same idea. 3M, it's quarterly. My 16% is an annual rate. I'm going to take that and divide it by 4 to get my 0.04. It's growing at a rate of 1% per quarter, so I don't have to touch my growth rate. And I plug it into my growing annuity formula, 1 minus 1.01 divided by 1.04, that whole fraction to the power of 60, because I've got 4 quarters per year for the next 15 years. Solve it up, and what do you see? Right off the gate, you can see that when we have growing cash flows, if the cash flows grow by 1% per quarter, the present value of those cash flows is considerably higher than if we have cash flows that are still pretty large. 3M a quarter is still a pretty good cash flow, but it's not growing. So hopefully we can kind of see how the growth rate is really going to affect our valuation. And that's an important concept for us to understand and for us to be able to apply